easy go.
I'm over here stroking my...
Every atom in the universe is held together by one of nature's most powerful forces, nuclear binding energy. It's the invisible glue that keeps the nucleus stable, and when that balance is disrupted, we see one of the most fascinating processes in physics, radioactive decay. But understanding nuclear binding is not just about physics, it's about understanding the forces that literally hold matter together.
Nuclear binding energy is the energy that keeps protons and neutrons together in the nucleus. It is caused by a nuclear force that hold the protons and nuclei. It's determined by the amount of protons and neutrons in the atom and stops electromagnetic repulsion from tearing apart the nucleus due to the protons repelling each other. Higher binding energy means the nucleus is more stable and it is released during decay.
The history and origins of the idea of nuclear binding go a while back, all the way to 1905. When Albert Einstein and his theory of mass-energy equivalence proved the theoretical foundation for understanding how mass is converted to energy in nuclear reactions. Then, in 1919, Francis Aston's invention of the mass spectrometer allowed him to discover that a helium nucleus is lighter than 4 hydrogen nuclei, which led to the prediction that fusion of hydrogen into helium could be the source of stellar energy. In 1932, James Chadwick was doing experiments, which included firing alpha radiation at beryllium sheets, which led to the production of uncharged penetrating radiation. He concluded that the unusual radiation consisted of uncharged particles having the same mass as a proton, which led to the discovery of the now named neutron. These neutrons were discovered to have a vital role in binding the center of the atom together.
Nuclear binding is represented by the equation E equals mc squared, which can be expanded into this equation, where the binding energy of an atom equals the number of neutrons times the mass of the neutron plus the number of protons and the mass of hydrogen, 1, minus the atomic mass of the atom times the speed of light squared.
While the inner workings and equations of nuclear binding are fascinating, you may be wondering how this idea actually applies to real life.
Nuclear binding is used in the real world as a large source of energy storage because nuclear binding energy is very large and can be released through the use of fission, which is used in nuclear reactors to produce a lot of power. Nuclear binding energy is also used to form atoms in like stars and things because it keeps the atom together.
And perhaps the most famous instance of the idea of nuclear binding application.
So a pretty common use of nuclear binding that you may have heard of is called the atomic bomb. So an atomic bomb is directly related to nuclear binding energy, which is released when a heavy atomic nucleus is split using nuclear fission or when light nuclei are fused together, which is called fusion. The immense energy in an atomic bomb is released because of the resulting more stable nuclei have slightly less mass than the original nucleus. This missing mass is then converted into a tremendous amount of energy according to Einstein's equation, E equals mc squared.
As you can see, there are many applications that can be explored with the concept of nuclear binding. Understanding nuclear binding gives us a clearer picture of what holds an atom's nucleus together, but this same concept also helps us explain what happens when those forces aren't strong enough. When a nucleus doesn't have the right balance of binding energy to stay stable, it can begin to change on its own. And that's where radioactive decay comes in. But what exactly is radioactive decay?
Intro into radioactive decay. Radioactive decay is the process by which an unstable atomic nucleus spontaneously loses energy by emitting ionizing radiation such as alpha particles, beta particles, or gamma rays. As previously stated, the main types of radioactive decay are alpha decay, beta decay, and gamma decay. Alpha decay emits an alpha particle, 2 protons, and 2 neutrons. Beta decay emits a beta particle, an electron, and a positron. Gamma decay releases high-energy gamma rays. There are also other types, such as positron emission and electron capture, that involves the nucleus emitting a positron or capturing an electron, respectively.
To explore the history of radioactive decay, we have to go all the way to 1896 in Paris, France. Physicist Henri Becquerel was experimenting with phosphorescent materials when he found that uranium salts would emit radiation even without sunlight. He initially thought that the uranium was absorbing energy from the sun and re-emitting it, but he'd soon discovered that the emission was happening even on overcast days. In 1898, Marie and Pierre Curie began investigating these rays, later coining the term radioactivity. Then in 1902, Ernest Rutherford and Frederick Soddy showed that radioactivity was a result of atoms of one element transforming into atoms of another element. They formulated the law of radioactive decay, which states that a fixed fraction of an element decays in a given unit of time.
As stated with this equation, given a sample of radioactive material, we measure the disintegrations or decays per unit time, which we define as activity. If we have n unstable atoms of material, the activity R is given by the derivative of n over t, where n is the unstable atoms, numbers of unstable atoms, d is time, which equals R. If n is the number of radioactive nuclei in the sample at the time t, and lambda, called the decay constant, is the probability per unit time that any given nucleus will decay, then the activity is represented by.
Now that we've looked at the mathematical form of decay and how the number of nuclei decrease over time, this idea can become even more intuitive. Instead of focusing on the full equation, scientists often use a simpler measure: half-life.
Half-life can be described as the amount of time it takes for a quantity of a substance to decay to half of its initial amount. Used to describe radioactive decay, where it is the time for half the atoms of the radioactive isotope to decay into a different element.
The inner workings of the half-life equations are actually quite interesting.
Instead of regular decomposition, when we're referring to half-life, we're essentially referring to half of that composition. So with our previously discussed decay law, we have it, which leads to this equation. We then apply the natural log to each side of the equation, and then we end up with the final equation for half-life.
Half-life and radioactive decay in general have many uses and applications in the real world, not to mention a multi-billion-dollar gaming franchise.
In real life, there are several examples of radioactive decay around us. Smoke detectors. Many household smoke detectors use a small amount of radioactive isotope to ionize the air, which triggers the alarm when smoke particles disrupt the ionization. Nuclear power. Radioactive decay provides the heat to produce steam and generate electricity in nuclear power plants. Radioactivity can be used to make useful energy for human purposes. One example is the radioisotope thermoelectric generator, or RTG, which uses radioactive decay to make electricity for satellites, space probes, among other things.
Now that we've seen how half-life is an essential element in modern-day research and understanding, we can bring everything together by looking at how these ideas play a bigger part into the world of nuclear physics.
Nuclear binding and radioactive decay are useful in physics because they allow the use of quantum mechanics and detail how atoms are made and work, while also leading to the creation of particle accelerators and the ability to collect very accurate atomic mass measurements.
Some practical applications of radioactive decay and nuclear binding include medical imaging, cancer treatment, such as PET scans and radiation therapy, carbon dating and geological age determination, nuclear power, and generation through fission.
These ideas are essential concepts in physics because they explain how atomic nuclei stay together and why some nuclei naturally transform over time. Understanding these processes helps us scientists harness nuclear energy, develop medical imaging and treatments, and then also study the origins of the elements of the universe.